They're organized in the, like I say, in the McDonald laboratory there. So 3 of us are theorists, and the rest are experimentalists. And we have, of course, a strong contingent of students from the lab here, whom many of you might have met also. Before I get started, though, I want to repeat something I heard a couple times yesterday, that this is a lecture, not a talk. So let's have a discussion, okay? If I don't get through all my slides, I'm not upset, it's okay. So stop me, slow me down, ask me questions, raise your hand, you know, that sort of thing. I really want you guys to take something away from it. I'm not trying to impress you with all my stuff, so like I say, if we don't get through it all, it's okay. Also, and I apologize if you guys did this before, but I know some of you actually aren't from Stron-Field physics background, so if you aren't, can you just raise your hand? Okay. So that's a few of you. So feel free, you guys should feel free also to ask questions. I'm hopefully pitching this at a level that everybody will benefit from. Now, what I'm going to talk about, and it's in a little bit different order than I told Hossein, so, but I thought this order might fit better with what other folks have talked about. And what I'm going to talk about is Stron-Field multicolor coherent control. Now, those words sound a little bit different than what people have been talking about, but I'll show you it's really the same stuff. And my subtitle is Putting the Photons Back in Stron-Field Physics. We've heard a lot about, we've heard a lot about 3-step models in the field and trajectories. You won't hear any of that in my talk, okay? I'm a theorist, I should have mentioned that probably. I'm a theorist. I like quantum mechanics, so I look for quantum mechanical explanations of things, not classical, okay? I want to get to the point where the simple interpretation is the quantum mechanical one, not the classical one, okay? Because I think when we get to that point, then we're going to start being able to use quantum mechanics to do things that we want. When that becomes our intuition, we'll be able to use it and manipulate it and all of those things much more effectively, okay? That's just my personal bias. So, I like to start with this, especially like in colloquia, because that usually gets people's attention, right? Einstein was wrong. What the heck do I mean by that? Well, Einstein, of course, told us about the photoelectric effect, and when you shine light on matter, you get electrons out. We all learned this in our, I don't know, beginning physics. We call it modern physics in most US curricula. And what you typically learn in the textbook, and I don't know if Einstein actually said it this way, because I didn't read his original paper, but what we learned in the photoelectric effect, the energy of the electron is the energy of the photon minus the work function, the ionization potential. We also learned that that energy does not depend on the intensity of the light. Moreover, there is a minimum frequency for that light coming in, okay? Because if h bar omega is not bigger than phi, then the work function, the ionization potential, you aren't going to get any electrons out. Well, I imagine by now, having heard many talks already, that you understand that that's not exactly true, okay? These are spectra, ATI spectra, meaning photoelectron spectra by shining strong lasers on an atom. I don't remember which one this is, argon maybe. This is from Gerhard Paulus from many years ago. And you can see all of these peaks, of course, are the ATI peaks. They're separated by 1 photon's worth of energy. So you absorb the right number of photons to get into continuum, then you keep absorbing photons, okay? Well, that sort of puts the lie to this photoelectric effect, at least as stated this way. This is a 1 photon effect, that's the key point. This is 1 photon, these are many photons. So in that case, we should modify all the rules for the photoelectric effect, that the energies actually can be obtained, the energy of the free electron can be had from absorption of many photons, okay? And that the energy does not exactly depend on the intensity of the light, okay? Or it does depend on the intensity of the light. And that there's not a minimum omega, because you can absorb 3 photons, or 10, or 50 in principle, and still get electrons out, okay? So that's the difference between, and we've heard it many times already, between sort of standard photoabsorption spectroscopy traditionally done for decades, and the multi-photon sort of effects that we're talking about in Stron-Field. Okay? Now, you don't just see these photon peaks in single fragmentation and simple ionization. What I'm showing here are some pictures from a paper that I wrote a while ago with Lars and one of his students and one of my students for ionization, in fact, dissociative ionization of H2+. So you take H2+ and you shine a strong field on it, and you break it into all its pieces. Okay? And what we learn is that the same sort of energy conservation expression still applies. That all the relative energy finally, between all these fragments, has to be the energy of all the photons absorbed minus whatever the initial energy was. Okay? And that means that if you plot the joint energy spectrum as a function of the electron energy and the relative nuclear energy, you get these lines. Okay? Those lines are the multi-photon lines. So the system absorbs 15 photons, and that energy gets shared between the electron going away and the nuclei going away. Okay? But there's still only so much energy available, and that's the energy given by energy conservation. So that same sort of multi-photon effect we saw in ATI applies when you have more particles in the final state. Okay? And that's, because it's just simple energy conservation, you can see that's nothing particularly special to this system or any system in particular. Okay? This energy conservation idea is going to work in essentially all cases, no matter how many particles you have in the final state. Okay? Now, whether you see these peaks or not depends somewhat on the details of the pulse itself, of the laser pulse. Okay? But we can talk about that a little later. But again, this I should have mentioned. These are calculations. These are theory that we did. And then Reinhardt Turner, oh yeah, here it is, did an experiment. Now, he didn't do the experiment corresponding exactly to the calculation we did. He did H2 plus a strong field and measured the outgoing hydrogen atoms, neutral, a proton and an electron. Okay? But that's still 3 particles in the final state. And I said it's only energy conservation, so it doesn't really matter what those 3 particles are. If you measure all their energy and you plot it, you're going to see these multi-photon peaks. And so the experiment saw exactly that. Okay? And we expect to see that essentially in any system. Okay? So the thing that I like to think about these kinds of plots is they give us a natural way to look at more complicated systems, because this line is a line of fixed total energy. So if you look along this line and see where the maxima is, that tells you how the energy was shared between, say, the electrons and the nuclei. So in this case, this is the nuclear axis, H plus H plus. In other words, hydrogen plus proton. Okay? And this is the electron axis. So this says the peak is closer to this side, so the electron energy was low, and, well, the scales are different, so that's actually about 2 eV and that's about 2 eV. So they both took away about the same amount of energy. Okay? But what I'd really like to see, and this is the coherent control aspect, is can we move that blob around? Can we force the electron to take away more energy? Okay? Can we force the electron, nuclei to take away 0, the electron to take away 0? That's the coherent control aspect. Can we manipulate the system at a quantum mechanical level by shining the light on it? Okay? And that's, of course, not just our goal. That's the goal of basically everybody who's talked here when they've talked about 2-color kinds of processes to manipulate harmonic generation, to manipulate whatever it was. That's coherent control. You're trying to adjust the light to get an outcome that you want. Okay? So typically when people talk about the harmonic generation and things like that, they don't call it coherent control. Coherent control is language that comes more from, say, the chemistry side, and controlling things like the nuclear motion, chemical reactions. Okay? And it's coherent control, and maybe that's my next slide. Let me just go here. It's coherent control because it's fundamentally a quantum mechanical thing. So the coherent means quantum mechanical. That's what they're really implying with that statement. And the idea is that you just want to set up the Young's double slit experiment. Okay? You want to have 2 or more pathways, and you want to, control the relative phase between them. So we know the classical, everybody I think knows the classical Young's double slit. You have a light source, you have 2 pinholes, that provides 2 different pathways over to your screen, and you see this interference pattern over there. And that interference pattern, of course, is controlled by the relative phase along those 2 paths. And as you scan that point along here, that phase difference will change. Okay? And that's what gives you the interference. And it looks more or less like a cosine or sine squared of the phase difference. Okay? In a quantum system, we have exactly the same thing. So you start from, let's imagine in this case, say an atomic problem. You have one bound state energy level and another bound state energy level. Let's say that you go from this state to that state with 1 photon, or you go from there to there with 3 photons. Okay? That's 2 different pathways now. And so those pathways can interfere, and if you can control the phase of those pathways, then you can control how much gets to the excited state. Okay? So the probability to be in that excited state is the amplitude for pathway 1. So this is the amplitude in the phase for that pathway. Amplitude in phase for the pathway 2. And of course the probability is the coherent square of those things. Okay? Yeah?
Why does it, in your graph, it looks like phi1 equals phi2?
Which one? This one or that one?
Well, the blue arrow is the sum of the 3 red arrows.
But that's just the energy. That's not the phase.
Okay.
So we need them to go to the same state, so they have to have the same energy. Because how do you get interference? You have to have 2 indistinguishable ways to go from the initial state to the final state. And the final state has to be the same. Otherwise you don't get interference. Okay? So the energies have to match, and that's the key. That is a good point. But the phase for that amplitude doesn't have to be the same. Okay? And so we have these 2 pathways. We have a probability that looks like that. And of course you expand it, and you get the interference term. Okay? And by the way, this is classic Brummer-Shapiro control. Okay? In the coherent control community, that's the names usually attached to this idea. Now, I didn't actually randomly choose 1 and 3 photons either, because if this is an atom, for instance, then these states have parity. Okay? And so to go to the same final state, dipole selection rules apply. And we know that if we start, let's say, in the ground state, even parity, for instance, we absorb 1 photon, what's the parity of the final state? Odd. Okay? So if I'm going to go there with 1 photon, that has to be an odd state. So how many photons, if I'm going to go with more than 1, can I get to the same state with 2 photons?
No.
Because that's even parity, right? So I have to have 3. 3 is the minimum that I can have to get to the same state. Okay? Now, this expression, it's quantum mechanics, it's wave phenomena. Okay? But it also tells you, in a sense, and I'll preempt Paul a little bit, the answer for, can you measure the wave function? Well, that amplitude is effectively the wave function. Okay? Amplitude and phase together is really the wave function. Okay? So probabilities are what you can measure. Okay? So maybe I won't give my answer yet, I'll leave Paul's question intact, but to give you guys maybe a little bit more of a hint, that's what you can measure probabilities, so it looks like that. Okay? And if that's something like a wave function, what can you measure from there? Okay? But we're going to use this a lot because this is interference. That's fundamental quantum mechanics, that's coherent control. Okay? Now if you have a system like H2+, that isn't simple 2-level system, or discrete levels, where for instance you go from a bound state to a continuum state, and I hope Born, Oppenheimer and things like that are familiar enough that this plot makes sense to you guys. This would be the ground state potential, and so bound states lie in here. For instance, that would be the energy of 1. Above this threshold, it's all continuum state. So if you make a transition up here, the molecule falls apart. Okay? So if you start in this vibrational state, we can absorb 1 photon and get up into this continuum, or we can absorb 2 photons and get up into the same continuum. Okay? Now, if they end at the same energy, right, that's important, but they have different phases along the way, then this kind of relation still holds. You still have interference, and if you were to measure the fragments, the energy of the fragments out there, whoops, let me use this one. If you were to measure the energy of the fragments out there, starting from 0 and increasing, then you would see an interference pattern, okay? That interference pattern would be controlled by the relative phase of those 2 pathways, okay? Now, I hope you're paying attention. Now I have 1 photon and 2 photons. So can they interfere? Well, if I have 1 photon, the final parity is what? If I start from even parity. It's odd, right? So what's the final parity along this pathway? Even. Can they interfere? Who says yes? Who says no? Some of you aren't voting. In this case, the answer is yes. Why? Because they're at a continuum now. So at that energy, you have both even and odd states, okay? And what you measure out here is not the parity state. You actually measure, in this case, a proton and a hydrogen atom, which ends up being a superposition of those 2. And if you superpose even and odd parity states, what you get is a state with directionality, okay? And so what this process is actually telling us is we can control the directionality of the fragments by controlling the relative phase of those 2 pathways, okay? If we had 1 photon and 3 photons, we could control the yield of the fragments this way, okay? Yeah?
Perhaps another way of saying it is that you're not measuring the parities in reference state. You're measuring the direction in which they come out.
Exactly. No, that's a good point. We're measuring direction, not parity.
Because if you could measure the parities, then they wouldn't interfere.
That's right. That's right. If you could measure parities, they would not interfere. But that's not what we measure. And we'll use that a little later on very explicitly. So, good point. So what I want to talk about, the example I'll use for Stron-Field coherent control is the carrier envelope phase. And of course, that was one of the reasons I decided to talk about this today, was because we heard a lot about this already yesterday and a bit the day before probably. Okay? So everybody I think knows what carrier envelope phase is, but maybe for those of you not from Stron-Field, I'll just repeat this. The idea is that when you put matter in a laser field at optical wavelengths, the only thing that matters is the electric field. The magnetic field doesn't matter, okay? For all intents and purposes. So what we always write for the laser field is just the electric field piece as an envelope times some carrier, and that phase right there is exactly the carrier envelope phase, okay? And these are just 2 plots for a 5 femtosecond and 10 femtosecond 800 nanometer laser pulse at 2 phases. And you can see in this long pulse, the 2 phases, the peak field, for instance, is more or less the same. However, in the shorter pulse, the peak field is a bit different. And this is the usual argument for why there are CE phase effects. By the way, I'll say that a lot. Carrier envelope is CE phase, okay? Why there are CE phase effects is because we're in a very nonlinear regime and the peak field strengths are different, okay? So if you change the CE phase, you get different peak field strengths, you get dependence of the nonlinear processes on the field. Okay? That's the usual explanation. And since this is a lecture and you're students, I don't want to take advantage of you. What I'm going to tell you is my way of looking at it. Okay? My way hasn't really caught on. Okay? So, I don't use the standard sort of field description. Now, you'll hear some things that are similar. Tony talks about things in a similar way, but I wouldn't say that this picture is widespread. Okay? But there's nothing wrong with it. It's exact. Okay? There's no model, there's no approximation, it's exact. Just to give you a little bit of the history, at least in terms of the molecular problem, and you can't read that, can you? Because I can't read it. In 2004, we had this paper where we actually done a calculation for CE phase effects and H2 plus dissociation. Okay? At this point, C phase effects were known, but mostly in ionization problems, ATI spectra. Garrett Paulus had done a lot of work, for instance, and seen that you could control the directionality of the electron using the CE phase. Okay? You can make it go right or left, depending on your choice. And so we wanted to look at this process, just dissociation of H2 plus into a proton plus hydrogen. Could you make the proton go right? Could you make it go left? Okay? And we saw that indeed you could, as a function of CE phase. You can see that the two channels, proton plus hydrogen or hydrogen plus proton, that means right and left, we could change over a big range. And I'll also point this out, that when we say control, all we mean is that the process depends on that parameter, right? If a process depends on a parameter, then in principle at least, you can turn it around and adjust the parameter to control and get the answer you want, okay? So these processes depended on the C phase. Now, 2 years later, the experimentalists caught up and did a measurement and saw in dissociation, Stron-Field dissociation of D2, they saw directionality plotted using this asymmetry parameter. However, I will point out that this is actually a different process. Okay? They started from D2 neutral, we started from H2 plus. Now the D's and the H's aren't the important difference. It's the charge state that's the difference. Okay? You'll also notice that I don't show energies here, sorry. Their energies actually are much larger than what we were looking at. If you wanted to try to compare these, you should be looking down at, I think it's these energies. Okay? But because they started from a different system than we did, you're going to see slightly different answers. Okay? Now, we did a little bit more work. This was 2012. We showed how we can enhance these relatively small controls, small degrees of control, because you'll notice this asymmetry parameter, and let's just take a second to think about what that can do. This asymmetry parameter can range from -1 to +1. So if you can send everything one direction, that would be, for instance, -1, or let's see, if it's over here, it would be +1. If you could send everything the other direction, that would be -1. Okay? And that's why we use this normalized asymmetry parameter, just to tell you sort of a relative measure of how well we're doing. But you can see in this plot, this experimental plot, ranges from -0.2 to 0.2. So that's not actually a huge degree of control. Okay? And if we go back, we didn't plot asymmetries, but you can see it ranges, probably the average is about 0.12. This is a probability. So 0.06 out of 0.12, sort of 0.5-ish numbers. But here, we increased the contrast by quite a lot. Okay? And this is still for H2 plus. We just,
You say asymmetries, what is the asymmetry in?
Let me go back. So here's the process we're looking at. H2 plus, you shine a strong laser on it, it breaks apart into a proton and a hydrogen. Okay? So you can have and they can measure the fragments, and they can measure the momentum distribution of those fragments. Okay? So, you can have a certain fraction of the fragments, certain fraction of the events where the proton goes this way, which means the hydrogen goes that way. But in the other part of the events, the proton will go this way, the hydrogen will go that way. So the directionality is essentially which direction does the proton go. Okay? And so the asymmetry, too many buttons, is just measuring that difference, taking how much goes this way minus how much goes that way, dividing by the sum to normalize it. Okay? So in this example, we managed to enhance it from doing nothing to our preparation of the system by about a factor of 10, it turns out. Now, I don't want to dwell on this because I want to get to the other stuff, so let me move through that a little bit and talk about the main point here. And that is that, from our point of view, all C phase effects can be thought of as a result of interference of different end photon amplitudes. okay? So instead of thinking about the field, we're thinking about photons, okay? When you think about photons, it's in a sense a time-independent kind of a picture. It's sort of a frequency space picture rather than a time domain picture, okay? And the way this comes about, here's a couple papers if you want to read where we started with these ideas. What we want to solve is the time-dependent Schrodinger equation, okay? That's what describes all of this. Time-dependent Schrodinger equation can be described in terms of the field-free piece and a dipole interaction, okay? So this is the dipole of the system. This is just the field, okay? And here's the C phase. And the key point, the key observation, and the only observation we really need, is that this equation is periodic in phi. This Hamiltonian is periodic in phi. That means the solutions have to also be periodic in phi. However, if they're periodic in phi, we can use a Fourier series to represent that C phase dependence. So we take the exact solution and we expand it in this Fourier series, and that's exact. Okay? And that's really all there is to this. The rest of it just follows from that observation. Okay? And I want to emphasize the simplicity here. So I'm going to derive this result on the board. Okay? I'm going to derive what we need on the board. So we're starting from I ddt psi, trying to match the notation, h naught minus e naught dot d cosine omega t plus phi psi. Okay? Now we say psi is this Fourier series. Okay? And all we have to do is substitute this into there. Okay? So we have sum over n, I, e to the I n phi, d dt psi n, h naught minus, now cosine omega t plus phi is e to the I omega t plus I phi divided by 2 times sum e to the I n phi psi n. All right? Okay, so now we simplify. How do we simplify? Well, the e to the I n phis are linearly independent, right? That means the coefficient of e to the I n phi on both sides has to be the same. Okay? So all we have to do is match the coefficient, let's say, of e to the I m phi on both sides, and that will be the equation for the psi n's. Okay? So on the left, we'll have I ddt psi m, h naught psi m, minus e naught dot d over 2. Now, we have an e to the I phi and an e to the I n phi. So that's e to the I n plus 1 phi. And n plus 1 better be equal to m. So that means this is e to the I omega t psi m minus 1. Right? Plus e to the minus I omega t psi m plus 1, doing the same on the other term. Okay? So that's it. That's the equation for these amplitudes. And this is the equation that we will use to understand the rest of this. Any questions about that? Yeah?
Do you have equations for the Maxwell equations? Do you have equations for the photons, or you just?
No. Yeah. This is getting at an important equation, an important question. I said, I'm going to put the photons back in, and I've said these are photons. What in the world do I mean by photons? Okay? I don't mean that I'm going to keep track of the field in a quantized way, the laser field in a quantized way. I don't mean that. Okay? In Stron-Field physics, when we say photons, we never mean anything like that. Okay? In Stron-Field physics, when we say photons, we mean something that has energy h bar omega. That's it. Okay? Now, to be honest, I think there likely is a deeper connection between the CE phase here and photons, because what does this expression say? I mean, this is a Fourier transform from phi space to n. That's the key point of this, okay? But I would have to solve, this represents coupled equations, because m ranges over all possible values from minus infinity to plus infinity in principle. Okay, so I turned it into coupled equations, which isn't computationally such a huge gain, okay? So no, to be honest, I won't say it that way. We've solved this equation once, okay?
Now, I'm talking about the normalization of your wave.
Oh, the normalization of the wave function is easy. I mean, this is normalized, right? So this is, yeah, I mean, that's the only normalization we require, that is required, okay? So this sum has to be normalized in the same way, okay? Now, we can do one more step, and that is to define, we can define a new function, phi m is e to the I omega t psi m. And we're always free to do that, right? I've just defined a new, I mean, these things are time-dependent functions. I've just defined a new time-dependent function. I can always do that. And if I substitute that in there, what we'll find is we get rid of these factors too. But otherwise the equation is just an equation for phi's. I'll show that one in a minute, okay? So the real point here, we're going to use this for interpretation. Yeah.
So what's the physics of this phi m? Because for given...
Of this one?
Yes. For
I'll get to that one in a minute.
Spaces, so how can you achieve?
Say it again. Okay.
I mean, for given force, the base phi is fixed.
Ah, but
So
here,
how can you understand this phi m in this case?
okay, I'll answer most of your question on the later slides. Part of your question I'll answer now. This equation for the psi m's or psi n's doesn't have a phi in it. All it has is the pulse envelope and of course the frequency, right? So I solved this equation once and I can construct all the pulses that have this envelope and this frequency for any C phase. Okay, that's what this relation allows me to do. I solve this equation once, given a pulse and a frequency. I can construct all solutions for all C phases of that pulse here. Okay? Yeah.
So the very last equation, that's basically going into the direction picture?
Oh, this one?
Yeah.
No, it's kind of the opposite. You're coming from the interaction picture. Let me advance. I'll show you the equation. I'll make it easier to say. So that top equation is the equation for phi. Okay? And oh, I messed up. There should be an n in here. I forgot the n, or the m in this case. I m omega t. Okay? But it's like going to the interaction representation, except we're going the opposite direction, right? Because in that equation, we just had h naught psi m. In this one, we get h naught minus n omega. So, in a sense, this is the energy of the photons. Okay? So we're putting it back in. Going to the interaction representation would normally take that away.
Okay, then, sorry.
Go ahead.
If you look at the second equation, that you see that's some kind of,
This one?
yeah, some kind of interaction picture in terms of the phase speed of time.
Well, this equation still depends on time. So it's not instead of time.
Right. So the second equation would be you go into the interaction picture in terms of the phase. You got the same transformation.
Well, but I mean, there's in terms of the phase.
So it's not a normal interaction picture, but
There is a connection, and I'm not sure that's it.
Okay.
And another question?
Back to my previous one. So
Okay.
do you have a classical equation for the photons? I mean the
Here, the electric field is given here. It's fixed. Okay, and so it's purely classical. It does solve Maxwell's equations, but it doesn't know about the atom or molecule at all. So it's unchanged. Okay, if you want to think about it that way. So it's not like what Ken was telling you about the coupled system. This would be completely uncoupled. The laser field is given. We don't follow what happens to the light at all. Okay? You couldn't be so large.
So it's more general comment also in relation to this lecture.
Yeah.
So maybe, I don't know, if you find that it would be helpful just to mention Floki theory and Bloch theorem. It's kind of related to this idea about using the periodicity.
True.
Maybe
So-
some students know about that.
It raises the question about the Floquet theorem, and to be honest, I purposely left it out because in a sense it confuses the issue, because this is not Floquet.
No, but it's still the Fourier decomposition is...
True. Let me say it this way. In my next lecture, I'll tell you about Floquet. Okay? I want to separate the concepts in time so they don't confuse you. But it's true. So think of that as the sort of forewarning that we will talk about Floquet, which is a similar idea but different. Okay? This is not Floquet. What I've shown you so far, this equation is exact. No approximations, right?
So
Yeah.
for Floquet, you assume that your field is constant. I mean, it doesn't have an envelope. And
That's right. That's right.
do you assume like an envelope here, or?
In what I'm doing?
Yeah.
Absolutely. That's what E naught of t is. That's the envelope function. So this works for pulses exactly. There's no approximation.
Okay, look, can you extend Floquet to this case when you have an envelope, or just for constant driving?
There are various extensions of Floquet to having an envelope, but again, they're related, but they look slightly different than this. Okay. Yeah.
Before the Hamiltonian is periodic and the results should be yes. And then because of the linearity dependence, you omit it, and the final equation, it does not depend on phi, and what is it? The problem is periodic in phase, and you are looking at CP effects, and the equation does not depend on phase.
But that's the beauty of it. It doesn't depend on phase. So if I solve this one, I can get all C phase dependence exactly with this equation. Once I know the size, I have all the C phase dependence. Right? That's the beauty of it, in my mind. Okay? Otherwise, I have to solve this equation for a bunch of different phi's.
I could add that this is exactly the same problem, except you replace t by x as diffraction by periodic potential. So you get the Raman-Nast solutions, right?
Sure.
Yeah.
Sure. And again, just since Floquet and these other sort of issues were brought up, I'll point out Floquet uses the periodicity in time. I'm using the periodicity in the phase. Okay? One key difference. For the phase, there is no derivative in here. For the time, there is a derivative. So that's it's a mathematical distinction, but an important one. Okay? For periodicity in phi, I don't need the Floquet theorem. But like I say, the rest of it follows exactly. Now, because of this equation, and by the way, I will point out that if there is no envelope, this is the Floquet equation. If E naught is constant in time, this is the Floquet equation. And there's one way that we can make the connection that omega is really, or n, is really the number of photons. Okay? There's one way that we can make the interpretation that psi n or phi n is an n-photon amplitude. Okay? Was there another question back there? Okay, there's one up here. Yeah.
You're saying that your top equation there is exact,
Yes.
but you're also saying that you're not accounting for the changes in the field that arise when electrons are freed.
Oh no, I mean electrons can be free. That's not the problem. What's not accounted for is the change in the field, the light field. Okay.
Oh, you mean you're not accounting for the fact that you're losing the photons?
Right.
Okay.
Or that I'm generating new frequencies.
Yeah.
Yeah. That part is not accounted for. That's what he was asking about. Was am I following the photons? No, I'm not following the photons dynamically. Okay. And so this is just bullet points basically repeating what I've said, is that this is an exact statement. These amplitudes don't themselves depend on the CE phase, which means the CE phase dependence is analytic and explicit. Okay? Moreover, this applies to any system. I didn't tell you what H naught was up here. I didn't tell you what the dipole was. So this is any system. And by the way, I wrote it in length gauge, for those of you who know what that means, but it applies equally well to velocity gauge, okay? So as long as you're working in the dipole approximation, this is fine. But as you guys know, you've taken quantum mechanics. Once you have the wave function, you have everything, right? Well, if the CE phase dependence is explicit, I have the wave function explicitly in terms of the CE phase. That means I can derive all the CE phase dependence I want, because I have the wave function. And that's what we'll do. We'll use this to derive general results to tell us about the CE phase dependence. So for example, and this comes back to Tony's comment, what we measure experimentally is the momentum. So in the P plus H problem, if you take the relative momentum between the P and the H, then we're measuring that momentum direction, okay? So we're taking the differential measurement of probability with respect to the momentum, the whole momentum vector, and you calculate that by taking our time-dependent wave function, projecting onto this scattering state that asymptotically is going out in one direction, okay? Just substitute in our expression for the time-dependent wave function and expand it out, okay? Very simple. So you see then that CE phase dependence, in other words, all the CE phase dependence is right here, remember? So for there to be CE phase dependence, n and n primes should not be the same, they should be different. And if n is the number of photons, that means different photon amplitudes have to interfere. More than that, these are the amplitudes. These matrix elements are the amplitudes, okay? And so for them to interfere, they have to contribute to the same direction, they have to have the same K, and if they have the same K, they can interfere, okay? So this is exactly the coherent control, Brewer-Shapiro, I don't know, two-pathway interference, Young's double slit, however you want to explain it, okay? That's exactly what this is. So CE phase effects are really coherent control, okay? Everybody good on this page? Because the rest of it is going to really use this idea. Yeah?
So for instance, something that was said a couple of times yesterday, which is no CE phase effects in one photon processes.
Right.
Right. So how do I see that from this expression?
Well, in that case, the only amplitude here that would be non-zero would be psi 1. Okay? And probably you presumably would have psi 0 left over because you don't get rid of the whole ground state. Okay? But if you look at, but psi 0 will just be a bound state typically. So let's say you start in a bound state, that will be 0 photons, 1 photon ionization, you get up to the continuum. Okay? And so the only thing with the direction here that's in the continuum will be psi 1. And so that would be 1 minus 1, no CE phase dependence. And all the other terms are 0. Yeah?
The simpler way of saying it is that for a one proton process, you have an amplitude and its complex conjugate, so the phase goes away.
Okay.
If you only have...
I mean, that's true, but I'm not sure that in here that I see that as easy.
Well, n equals n prime.
Right. That's what I said, I think. Okay. Okay. Okay.
So it's really the off-diagonal
Absolutely.
entries.
Right. It's different photon pathways interfering with a caveat. Yeah, that's right. Different photon pathways. Because n has to be different than n prime to have any CE phase effect left. Because if n equals n prime, this just reduces to 1. Yeah. Yeah.
But the person from that, you somehow see the CP effect.
Let me get to that in a minute. Other questions?
So then I would say that if I have an unlocked laser,
Yeah.
right, where phi is now a random variable shot to shot,
Right.
I integrate over phi.
Absolutely.
All the diagonal terms go away, and that's where the CE phase
Yes.
was.
And that's trivial to see when you have this expression. Yeah. So did everybody get that? Because sometimes when people do experiments, they don't control the CE phase, and the CE phase may change randomly from one pulse to the next. So the measurements are really a random distribution of CE phases. So how would you get the answer? Well, this is the observable, right? That's what you compare with the experiment. You compare the observable. And so if you want a random distribution, say the uniform distribution of CE phases, just average this over C phase, which means everything with n not equal to n prime goes away. So only the pieces with n equals n prime will survive. Okay? And again, that's one advantage in my mind of having an expression where these things are explicit, because you can do all those manipulations without solving any TDSE. Okay?
Can I ask one more question?
Yes?
So if you've done it, because I agree, computationally, this is not the way to go. I mean, because, for instance, if you imagine solving for 20 different CE phases, you could do that on 20 processors all at once.
Sure.
Whereas coupling 20 orders, right?
Doesn't scale the way. Yeah.
Okay, but this is still, let's say this is extremely useful. If you have the solution, like it's more if you've tried this,
Right.
if you now do the solution on 20 processors, get the answer for 20 different CE phases, can you unfold these?
Absolutely.
And have you tried that?
Yeah, we've done that.
That works.
So basically what you're saying is, we want that information. We can either solve this equation, or we can solve the original equation for this guy, and then use this relation to get the psi-ns. All you have to do is a Fourier transform in CE phase. And absolutely, we've done that. It works beautifully.
So then there's the whole Nyquist sampling and all that.
Absolutely. Actually, I wouldn't even worry about Nyquist sampling, because for the most part, we can get everything with 4 CE phase points. Because of aliasing and energy separation, we can separate all the different photons that way. I can tell you more detail what I mean by that later if you want. But yeah, I was going to mention that a little later, but this is a good point. This is a relation that goes both ways. It's exact. So if I have either one of them, I can get the other. Okay? And so if you want to learn about photon pathways, and by the way, this is a way to define a photon amplitude, which may not otherwise be such a clear thing to define. This is a way to define it. Okay? Moreover, this is a relation that holds it every time. That means even during a pulse it holds. So we can follow the photon amplitudes during the pulse and see how the 1 photon, 2 photon, 3 photon things get populated during the pulse. So it's an interesting way to follow the dynamics. However, one caution, during the pulse, your answer will be gauge dependent. Okay? You can define this is a perfect way to define it, but just be aware that during the pulse, everything, all of these things go away. They aren't gauge independent. Okay? But as many people have already plotted things like ionization probability as a function of time during the pulse, which is not gauge independent either, this is an equally good thing to look at. Okay? Now, so we have interference of these amplitudes. Let's look at a common observable, which is the CE phase-induced spatial asymmetry, which means that you just take whatever goes up minus whatever goes down at a given energy. Okay? Now, if you use the expression for the momentum distribution that I gave before, then you can simplify it to this kind of an answer. Okay? Sum over n even and n prime odd, and this E superscript and O superscript means even and odd parity. Okay? Even and odd parity. So what is this saying? This says that to see any CE phase dependence in the asymmetry, you need n different than n prime, but that's guaranteed because one's even and one's odd. But you also need an even parity state to contribute at a particular direction, and an odd parity state to contribute in the same direction. We already saw that example though. Okay? When you have dissociation or ionization, because remember, I'm giving molecular examples, but there's no specific system specified here. So everything I'm saying applies to ionization, dissociation, dissociative ionization, everything. Okay? Ionized DNA if you want. This will give you the answer. Okay? And that's the power of it. I don't solve it this way. I don't solve these equations, but I use it to guide my thinking. I use it to interpret. I use it to predict. Okay? But you'll also notice that the lowest order CE phase effect is when n and n prime differ by 1. Okay? So you'll get an e to the I phi. That would be like if 1 photon and 2 photon interfere. That would give you e to the I phi. Okay?
Brett, a quick question.
Yeah.
Before that. So, you wrote your field as a standard short pulse field
Yep.
there, and then for most fields, you don't have omega and 2 omega contained within that pulse.
You don't need it.
So go to this picture, right, you show omega and 2 omega.
Sure, but n and n prime can differ by 3 and 4. And so I'll show you, let me show you the picture and you'll see what I'm talking about. Okay? So the next picture, I think, addresses this question and an earlier question. And that is, how do we understand these C phase effects maybe in an energy picture? Because again, we're using photons, so we're implicitly in a frequency or energy domain sort of picture. So what I'm sketching here is energy here. This line would represent, for instance, the energy of the ground state. If you're sitting in the ground state and you absorb 1 photon, that's 1 arrow, 2 photons, 3 photons. 3 photons get you into the continuum because you're above 0 energy here, you're above threshold. And the peak that you would get in an ATI spectrum or something like that might look like this. Okay? Centered on the 3 photon energy with some width. But you would also get another one at 4 photons, another one at 5, another one at 6, and so on. Okay? Now 3 photons would put you in an odd parity state if you start in an even parity state. So 4 photons is even parity, odd parity, even parity. That's what the colors of these are supposed to remind you of. Okay? And remember, for spatial asymmetry, you need even parity to interfere with odd parity. Okay? Well, do we have any interference of even parity and odd parity here? What do you think? Who says yes? Who says no? Okay, again, most of you aren't voting. That's not an option. Okay? If they interfere, remember they have to have the same final momentum. That means they have to have the same final energy. And this is an energy axis. So for this odd parity to have the same energy as the even parity, we have to look there where they overlap, right? And yeah, there's a tiny little overlap there, but it's tiny. So in principle, yes, there's interference. In practice, it's really, really tiny. Okay? So I would give partial credit for both answers. Okay? So interference is possible only when these overlap. Now what I didn't say is the width of this peak is related to the bandwidth of the laser pulse. Okay, let's stick with transform limited for a second. Okay? For transform limited laser pulses, the width of these individual peaks are related to the bandwidth of the laser pulse. So to get them to overlap, clearly you need broader energy distributions. Okay? And how do you get a broader energy distribution? Shorter pulse, because you need a bigger bandwidth. Okay? So this leads to the conclusion that most people expect, is that interference is possible only when those overlap, which means short pulses. Okay? And of course the interference now is in these gray regions. But notice it's always in the exponential tail. It's always in the tail of this power spectrum. Okay? So for this reason, at least and this picture is sort of the approach from low intensities. This is sort of a lowest order perturbation theory kind of picture. Coming from that direction, you would expect C phase effects to always be small because they're always in the overlap of the tails. Okay? If you get to high enough intensity, these things start shifting around and really broadening and going crazy. The picture still holds, it's just not as easy to predict. And you can have larger C phase effects now. But we can also predict that if we were to look at the C phase dependence, you would only have terms like cosine and sine phi, cosine 3 phi, sine 3 phi. You would have the whole trigonometric series with odd frequencies. Okay? Now, if I take a survey of the C phase results that were available in March of 2014 anyway, so these are experiments. Okay? And I'll tell you without going through these in detail that all of these show exactly this cosine phi phase dependence. Okay? That would mean the period, so here's a phase axis from 0 to 4 pi, so 0 to 2 pi. 2 pi is the period, that's just cosine, or sine, right? If the period of this asymmetry, which is plotted here, is 2 pi, that's just cosine phi or sine phi. And my contention is that that's a trivial consequence. The cosine phi and sine phi is a trivial consequence. And I point that out because there are a number of theories, a number of models that claim that getting this cosine phi and sine phi agreement is a really good thing. I would contend that you can't help but get that if you mix even parity and odd parity. You have to get that. There's no choice. So getting the right periodicity says nothing about your model except that you mix two parities. Okay? If you really want to test it, what you need to get right, is the magnitude and phase of the C phase dependence. Okay? What does that mean? That means getting these guys right. Okay? Now, I'm running out of time, so let me go through this a little bit quicker. We've done it once, so it should be a little bit quicker. We can go through the same analysis for the yield, which relates to some of what Ken talked about and what he asked. So if we want to look at the yield and modulating the yield with CE phase, you can do exactly the same analysis. You get this sort of equation. The difference now is that n and n prime are any numbers, but these amplitudes, you have to have contributions from even parity at the same place as even parity, and odd parity at the same place as odd parity. Okay? So this is interference of even parity with itself and odd parity with itself. It's not even with odd like it was for the spatial asymmetry. But to get CE phase dependence, you need n to be different from n prime. So how does even parity interfere with itself? What's the minimum number of photons for that to happen? Well, 0 is the minimum number, but that gives you no CE phase dependence. So 2, exactly, 2 is the minimum number to get CE phase dependence. Okay? And so you expect, so here's the same kind of picture, schematic picture for the effect. You have narrow pulses, broad pulses. So that would be the spatial asymmetry between odd and even parity. Yield dependence of CE phase is down here where odd parity interferes with odd parity. That's down there. Or even parity with even parity. That's down there. So it's even smaller. It's even further out in the tails of the power spectrum. Okay? But if you have it, it's going to have periods in a Fourier series that are the even frequencies. Okay? And again, survey of experiments showing yield, CE phase dependent yields. And what you'll see, this is a range of, in this case, 2 pi. And so you have 2 periods there. That's exactly the cosine 2 phi kind of dependence. Okay? And all of these are consistent with that expression. Now, that raises, so we have a picture. We've explained things. Now let's try to predict things. Okay? So what else can we predict? One big question, or one question that came to us at least, was, do CE phase effects depend on the pulse length or the bandwidth? Okay? Most of the people arguing from the field picture would argue it's the pulse length, because you need the peak field to be very different. Okay? But from our picture, we're in energy domain, right? We said it's the overlap of the power spectrum. In that case, pulse length has nothing to do with this. We need to know about we need a broad power spectrum, but that's the bandwidth. Okay? So if it's just the bandwidth, that means we should be able to see CE phase effects even for long pulses, as long as they have a broad bandwidth. Okay? How do you get a long pulse with a broad bandwidth? Anybody? You chirp it, right? Because once you add chirp, the relation between bandwidth and pulse length gets relaxed at least. Okay? So we can do the calculation. So here's our dissociation of H2 plus again into a proton plus hydrogen atom as a function. So this is the KER spectrum, the energy spectrum. And along this axis is pulse length. Okay? The middle panel shows you what happens if you take just a transform limited pulse and look at CE phase effects. So this is the spatial asymmetry for a CE phase of 0. Okay? So you can see the spatial asymmetry normalized goes from -0.4 to 0.4. So you see spatial asymmetry in this particular case out to about a pulse length of say 20 femtoseconds. Okay? But if you positively chirp the pulse, but keep the bandwidth equal to a 5 femtosecond transform limited pulse, then you can see CE phase effects all the way out to 60 femtoseconds. Okay? And if you negatively chirp them, you can also see CE phase effects out to 60 femtoseconds. Okay? And for, this is 800 nanometer light, so 60 femtoseconds is how many cycles? 2.5 femtoseconds per cycle. We did the calculation and predicted this. We predicted it based on the model. Then we did TDSE to verify. And then the experimentalists got interested and did experiments to also verify. So this was an experiment, by the way. The experiments that I've shown are from my colleague Itzik's group. Okay? Several of his students are here representing the group, Payman and Travis and Bethany. Some of them were involved in these experiments. And you can see that there's CE phase effects in the symmetry for this process. 5 femtosecond transform limited, chirped out to 21 femtoseconds positively, or 21 negatively. And you can see there's CE phase effects here, right? Seeing red and blue stripes, that's CE phase effects. Red and blue stripes. And here they're fainter, but they're still there a little bit, okay? So it looks like bandwidth really is an important factor, not just the pulse length. Let me take a couple more minutes, because I want to address what Ken brought up. How can we use this picture to predict things for maybe more complicated systems? Well, I showed you this picture before. This was the multi-photon structure in dissociative ionization of H2. So let's say this is 3 photons and 4 photons and 5 photons and 6, for instance. Okay? Well, if we want to predict whether there's CE phase effects, what energies will they be in this picture? They have to be between these photon peaks, right? Because it has to be, say, 4 and 5 photon interference, so it has to be in there. So if you want to see a spatial asymmetry, it has to lie in there. What does spatial asymmetry mean for this system? It means the electron going a different direction than the proton. Okay? So if the proton goes this way, the electron can go the same way or the opposite way. That would be spatial asymmetry, and that would happen here, 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 or there. Okay? So clearly in this case, you need a much shorter pulse to be able to see it, because there's not much overlap there. Okay? And that's just what I see over on the side. Now, relating to some of the things that Ken brought up, this picture, if you replace H2 by helium and, the alpha particle and 2 electrons, the picture looks the same. Double ionization, the picture looks the same. Okay? And so if you wanted interference, say to control the yield of double ionization, well, this photon peak has to interfere with that photon peak. So you need a really short pulse or really broad bandwidth such that there's interference between this guy and this guy. Okay? Then you can control the yield. Okay? You can use that same kind of logic for understanding, for predicting CE phase effects in other systems. Now, yeah, there is more good stuff, but in terms of time, I should stop. Let me just say one more thing, because it again relates to what other people were talking about. We can do all the same things for 2 color fields, or 3 color, or 4, or 15,000, I don't care. Okay? If you can write a 2 color field like this, so this one has a phase and that one has a phase, well, this one could be the phase relative to that one, for instance. Well, if I can write it like that, then of course I can do a Fourier series, and I can do all the same analysis. So, Rabbit, the ATOS, AB, pulse train plus IR, all of those things can be analyzed exactly this way. Okay? We've done some of it. But I just want to point out that we can do the same kinds of things for other fields. Okay? I won't go through that in detail. Yeah, let me just finish by emphasizing this was an exact theory. There's no models, there's no approximations. We aren't using it as a computational tool primarily, but rather as an interpretational tool, a predictive tool. Okay? It's based on simple selection rules, dipole selection, photon number, energy conservation, things like that. Okay? And it can be generalized to other things. Now, I'll also mention maybe not having seen what Tony talked about, but if you take perturbation approximations to this, then I think that overlaps a lot with what Tony was talking about, or will talk about.
My lecture's on the web, you can look at it.
Okay, very good.
We covered this for first and second order forces.
Right, so this is the full sort of exact overarching treatment. If you do the first few terms, say with perturbation theory, that connects nicely with what other folks have talked about. Anyway, I better stop there. Thank you.
Thank you. Well, a fair number of questions. I think Brad prodded you to ask questions, but are there more?
I would just make a comment, a clarification. If
Yeah.
you go back to one of the last slides, I think it was under yield.
Oh, okay.
Where you showed the interference between the peaks. There.
Yeah, well, this one's for asymmetry, but,
Right.
okay.
Say symmetry. So I would just point out that this diagram should also include for the two-photon process, because the tail, the high-energy tail of the two-photon could be above threshold and cause interference.
Sure, and so, I mean,
So you
this
don't
one,
only start where the central frequency is above threshold.
oh, of course, no, this one could have a tail that extends over there, and that's this guy.
That's right.
Yeah, except in this case, that's actually 0 photon and 1 photon.
Right,
Okay,
right.
this
Zero
is-
photon could be absorption and emission.
Exactly.
Of two photons.
And by the way, that maybe is a good point to clarify. When I say 3 photons, that's the net. You could absorb 3, or you could absorb 4 and emit 1, or absorb 5 and emit 2, but that's the net number of photons, okay? And so, yeah, we could actually, from this peak, we could have the tail over here, and that's really what's giving these peaks. So if I were to show the photon peaks, they would lie in these empty areas, okay?
Yeah, go ahead.
They're fine.
And then you ask.
Always there are uncertainty principle between number of photon and phase. If you have information about the number of photon, you lose information about the phase. How is it here? I mean, you know the phase, you know the number of the photon. It's same.
But we don't know the number of photons, right?
You say, for example, for this phase, you have 3 photons.
No, I'm saying for a particular phase, I have 0, 1, 2, 3, 4, a whole distribution of photon
So there are a
contributions.
lot of possibilities.
Absolutely. Yeah, I mean, just like this picture, right? This sketch, I mean, there's several photon peaks contributing.
I'd be interested how you technically solve the Schrodinger equation for an H2 molecule. This sounds a bit complicated, but I'm Schrodinger to nuclear ion.
It is, and it's not a short answer, so maybe we can talk later. Yeah. I'll be here till the end of the workshop, so.
School.
School.
So maybe this is a good place to take a 5-minute break, and then we'll come back for the next lecture by Tony, who is not here. Okay. Thank you.